on August 25, 2012, at a distance of 121 astronomical units from Earth. NASA's Voyager 1 spacecraft crossed a boundary that no human-made object had ever reached: the Heliopause, the edge of the Sun's protective bubble. The place where the solar wind, stream of charged particles flowing outward from our star at 1 million miles per hour, collides with the interstellar medium and stops. The instruments aboard Voyager 1 recorded the transition in real time. The plasma density suddenly increased by a factor of 40. The magnetic field direction shifted, and the solar wind, which had been detectable for 35 years of flight, vanished completely. Voyager 1 had left the solar system, not in the sense of escaping the sun's gravitational influence, which extends trillions of miles into space, but in the sense of leaving the region dominated by the sun's activity, entering a space shaped by forces from other stars, other supernovae, other cosmic events that occurred millions of years before Earth even formed. And the spacecraft is still transmitting, still sending data back across 15 billion miles of space. A signal so faint, it arrives at Earth with 1/1000th of a watt of power, barely enough energy to flip a single bit of information every few seconds. But that signal contains measurements of a realm no human has ever observed: the space between stars, the cosmic ocean that separates our solar system from the rest of the galaxy. And what Voyager 1 found in that darkness was not emptiness. It was structure, magnetic fields, like shockwaves, regions where the density of matter changes abruptly, as if interstellar space has boundaries, invisible walls that separate one domain from another. We are not alone in the void. We are surrounded by an architecture we are only beginning to perceive. Voyager 1 and its twin, Voyager 2, are not recent missions. They were launched in 1977 during a rare planetary alignment that occurs once every 176 years, when Jupiter, Saturn, Uranus, and Neptune position themselves in a configuration that allows a spacecraft to visit all 4 worlds using gravity assists, slingshotting from one planet to the next without requiring additional fuel. The mission was called the Grand Tour, and it was humanity's first attempt to explore the outer solar system in detail. NASA engineer Gary Flandreau at the Jet Propulsion Laboratory calculated the trajectory in 1965, determining that a spacecraft launched in the late 1970s could visit all 4 gas giants. In a single 12-year journey, the opportunity would not return until 2153. Voyager 1 launched on September 5, 1977. Voyager 2 launched 16 days earlier, on August 20th, but followed a slower trajectory designed to visit Uranus and Neptune, planets Voyager 1 would not encounter. Both spacecraft carried identical instrument packages: cameras, spectrometers, magnetometers, plasma detectors, and cosmic ray sensors. And both carried the golden record, a 12-inch gold-plated copper disc containing sound and images from Earth, a message to any intelligence that might one day intercept the spacecraft drifting through interstellar space. Voyager 1 reached Jupiter in March 1979, capturing the first detailed images of the Great Red Spot, discovering active volcanoes on the Moon, Io, and measuring Jupiter's immense magnetic field. It reached Saturn in November 1980, photographing the planet's rings in unprecedented detail and discovering that the Moon, Titan, had a thick nitrogen atmosphere, and then it left. Flung outward by Saturn's gravity at a velocity of 38,000 miles per hour, Voyager 1 began its journey toward the edge of the solar system, a destination that would take another 32 years to reach. But the mission was never supposed to last that long. Voyager's instruments were designed to function for 5 years. The spacecraft's nuclear power source, a radioisotope thermoelectric generator, was expected to provide enough electricity for 12 years of operation at most. 48 years later, Voyager 1 is still functioning, still transmitting, still traveling deeper into interstellar space. The first sign that Voyager 1 was approaching the edge of the solar system came in 2004, when the spacecraft's low-energy charged particle instrument detected a decrease in the intensity of solar wind particles. The solar wind is a continuous stream of protons and electrons ejected from the sun's corona, blowing outward at speeds exceeding 1 million miles per hour, creating a bubble called the heliosphere that extends far beyond the orbits of the planets. But the solar wind does not extend forever. Eventually, it encounters the interstellar medium, the dilute gas that fills the space between stars, composed primarily of hydrogen atoms, helium, and trace amounts of heavier elements. And when the solar wind collides with the interstellar medium, it slows down, compresses, and forms a shock wave called the termination shock. Voyager 1 crossed the termination shock on December 16, 2004, at a distance of 94 astronomical units from the Sun. Physicist Timotheos Krimigas at Johns Hopkins University, principal investigator for the Low-Energy Charged Particle Instrument, analyzed the data and found that the solar wind had suddenly decelerated from supersonic to subsonic speeds, exactly as models predicted. But crossing the termination shock was not the same as leaving the solar system. Beyond the shock lies a region called the heliosheath, turbulent zone where the solar wind continues to flow outward, but is compressed and heated by the pressure of the interstellar medium. Voyager 1 would spend the next 8 years traversing this region, measuring its properties, searching for the final boundary. That boundary is the heliopause, the place where the solar wind stops entirely and the interstellar medium begins. In 2010, Voyager 1's plasma instrument failed, leaving the spacecraft unable to directly measure the velocity and density of charged particles around it. This was a critical loss. Without plasma measurements, scientists could not definitively determine when Voyager 1 crossed the heliopause, because the transition is defined by a change in plasma properties, not magnetic field or cosmic ray intensity. But physicist Edward Stone at Caltech, Voyager's project scientist since 1972, realized there was another way to detect the crossing. The heliopause should produce a sudden increase in plasma density, because the interstellar medium is denser than the heliosheath. And even without a functioning plasma instrument, that density could be inferred indirectly by measuring plasma oscillations. Ripples in the charged particle environment caused by solar eruptions or interstellar disturbances. In October 2012, the Sun released a coronal mass ejection, a massive burst of plasma that propagated outward through the solar system. When the eruption reached Voyager 1's location 13 months later, April 2013, it caused the surrounding plasma to oscillate at a frequency that depended on the plasma's density. Voyager's plasma wave instrument detected the oscillation, and the frequency revealed that the plasma density was 40 times higher than it had been in the heliosheath. This was the proof. Voyager 1 had crossed the heliopause, and by working backward from the detection date, Stone and his team determined that the crossing had occurred on August 25, 2012, making Voyager 1 the first human-made object to enter interstellar space. But interstellar space was not what anyone expected. Why does the region beyond the heliopause have structure? Till now, this looked like a boundary crossing, transition from one environment to another, spacecraft leaving the Sun's domain and entering the emptiness between stars. But it was not emptiness. Because in 2015, Voyager 1's instruments detected something that should not have been there, a magnetic field. Not the Sun's magnetic field, which should have ended at the heliopause. A different field, stronger, more organized, lined in a direction that did not point back toward the solar system. Physicist Leonard Berlanga at NASA's Goddard Space Flight Center analyzed the magnetometer data and found that the interstellar magnetic field was not uniform. It had boundaries, regions where the field strength increased or decreased abruptly, as if interstellar space is divided into domains, each with its own magnetic structure. This was unexpected. Interstellar medium was thought to be mostly uniform on scales smaller than a few light years, shaped primarily by the motion of the Sun through the galaxy and by distant supernova remnants. But Voyager 1 was detecting variations on scales of astronomical units, distances comparable to the size of the solar system. Berlanga proposed that the variations were caused by interstellar turbulence, chaotic motions in the galactic magnetic field driven by stellar winds, supernova shock waves, and the rotation of the Milky Way itself. The Sun moves through this turbulent medium at 19 kilometers per second, and as it does, it encounters regions of higher and lower density, stronger and weaker magnetic fields, creating the structure Voyager 1 was measuring. This is the hidden barrier. The assumption that interstellar space is smooth, because if the interstellar medium is turbulent, if it contains structure on small scales, then every star system is embedded in a unique environment shaped by the local magnetic field, the local density, and the local cosmic ray flux. And our solar system's environment is not constant. It changes as the Sun moves through the galaxy. In 2014, astrophysicist Priscilla Frisch at the University of Chicago published a study showing that the Sun is currently inside a region called the local interstellar cloud, a diffuse structure approximately 30 light-years across, composed of warm gas left over from a supernova explosion that occurred several million years ago. The local interstellar cloud is itself embedded in a larger structure called the local bubble, a cavity carved out by multiple supernovae that exploded within the past 10 million years. The boundaries of these structures are not sharp. They are transition zones where density, temperature, and magnetic field strength change gradually. And Voyager 1 is now measuring those transitions directly, providing the first insight of data about the interstellar medium's small-scale structure. But the most disturbing discovery came in 2020, when Voyager 1 detected an increase in cosmic ray intensity. Cosmic rays are high-energy particles, mostly protons, accelerated to nearly the speed of light by supernova shockwaves and other violent events. They permeate the galaxy, and their intensity is highest in interstellar space, where the Sun's magnetic field no longer deflects them. The increase was expected. What was not expected was that the cosmic ray intensity fluctuated. It did not rise smoothly and plateau at a constant level. It varied, increasing and decreasing on timescales of months, as if Voyager 1 was passing through regions with different cosmic ray densities. Physicist Jamie Rankin at Princeton University analyzed the fluctuations and found that they correlated with changes in the magnetic field direction. When the field aligned in certain directions, cosmic ray intensity increased. When it aligned differently, intensity decreased. This suggested that the interstellar magnetic field is channeling cosmic rays, funneling them along field lines like rivers flowing through a landscape, which means interstellar space is not isotropic, it is preferred directions. Pathways where particles flow more easily, and barriers where they are deflected. Why does the space between stars have invisible highways? In November 2018, Voyager 2 crossed the Heliopause at a different location than Voyager 1, providing the first opportunity to compare interstellar conditions at two separate points. Voyager 2 was launched before Voyager 1 but followed a slower trajectory, visiting Uranus in 1986 and Neptune in 1989 before heading toward the edge of the solar system. Voyager 2's crossing occurred at 119 astronomical units from the Sun, slightly closer than Voyager 1's crossing at 121 astronomical units. But the critical difference was direction. Voyager 1 crossed the Heliopause in the northern hemisphere of the heliosphere, the region ahead of the Sun's motion through the galaxy. Voyager 2 crossed in the southern hemisphere at an angle offset by about 60 degrees. Physicist Edward Stone compared the data from both spacecraft and found that the Heliopause is not spherical. It is asymmetric, compressed in the direction the Sun is moving and elongated in the opposite direction, shaped like a comet's tail. This asymmetry is caused by the interstellar wind, the relative motion between the Sun and the surrounding interstellar medium. But the asymmetry was more extreme than models predicted. The Heliopause was thinner and more distorted, suggesting that the interstellar magnetic field is stronger than previously estimated, exerting more pressure on the heliosphere than the solar wind alone can counteract. And critically, Voyager 2's plasma instrument was still functioning, unlike Voyager 1, which had lost plasma measurements in 2010. Voyager 2 could directly measure the plasma density and velocity as it crossed the Heliopause. Physicist John Richardson at MIT analyzed the data and found that the plasma density increased by a factor of 20, confirming the transition into interstellar space. But Richardson also found that the plasma temperature was higher than expected. The interstellar medium just beyond the Heliopause was heated to approximately 30,000 Kelvin, far hotter than the 6,000 Kelvin temperature of the heliosheath. This suggested that the Heliopause itself is not a passive boundary, but an active shock front, where the collision between the solar wind and the interstellar medium releases energy, heating the surrounding plasma. And then, in 2021, Voyager 1 detected a hum, faint continuous tone at a frequency of 3 kHz, recorded by the plasma wave instrument. Physicist Stella Acker at Cornell University analyzed the signal and determined that it was caused by plasma oscillations in the interstellar medium, driven by the thermal motion of electrons. This was the first detection of ambient interstellar plasma noise. the background vibration of charged particles in the space between stars, and the frequency of the hum revealed the plasma density with unprecedented precision, confirming that Voyager 1 was traveling through a region where the density was slowly increasing. From 0.05 particles per cubic centimeter in 2012 to 0.13 particles per cubic centimeter in 2021. The increase suggested that Voyager 1 is approaching the outer edge of the local interstellar cloud, where the density rises as the spacecraft moves toward the boundary between the cloud and the surrounding local bubble. This was proof that interstellar space is not static. It is structured, layered. It's filled with clouds and bubbles and shock waves left over from stellar explosions that occurred millions of years ago. And Voyager 1 is now mapping that structure, one measurement at a time, traveling deeper into a region no human will visit for centuries. On August 25, 2012, Voyager 1 left the solar system. Not by escaping the sun's gravity, which extends halfway to the nearest star, but by crossing the Heliopause, the boundary where the sun's influence ends and interstellar space begins. 14 years later, Voyager 1 is 163 astronomical units from Earth, traveling at 38,000 miles per hour, moving farther from home with every passing second. Its power supply is fading. Its instruments are failing one by one. By 2025, the spacecraft will no longer have enough electricity to operate its science instruments, and by 2030, it will go silent, drifting forever through the galaxy with no way to communicate what it sees. But in the 48 years since launch, Voyager 1 has transformed our understanding of the solar system's place in the galaxy. It revealed that the boundary between the sun's domain and interstellar space is not a wall, but a dynamic frontier, shaped by the collision of two winds, two plasmas, two magnetic fields. It discovered that interstellar space is not empty, but structured, filled with magnetic highways and density boundaries and shock waves from ancient supernova. And it proved that humanity can build machines that outlast their designers, continue functioning decades beyond their intended lifespan, that travel farther than any person will go in our lifetimes. Voyager 1 is now the most distant human-made object in existence. It will remain so for decades, possibly centuries, until another spacecraft surpasses it. And long after humanity's gone, long after, Earth has been consumed by the sun's red giant expansion 5 billion years from now, Voyager 1 will still be out there, drifting through the galaxy carrying the golden record, a message from a species, once looked up at the stars and wondered what lay beyond. And once you realize that Voyager 1 is our first ambassador to the galaxy, that it carries the only physical evidence of humanity's existence that will survive into the deep future, you start to understand the magnitude of what we have done. We have sent a piece of ourselves into the cosmos, not as conquerors, not as explorers seeking territory, but as witnesses, documenting the universe as it exists, one measurement at a time. Subscribe to Universe Uncovered, because the solar system is not our limit. It is our starting point, and we have already taken the first step into the darkness beyond.